Going to be all about oxidation numbers today, and we're going to start off with assigning oxidation numbers. I made a bit of a hash of explaining this last time. I think I tried to squeeze it into a part of a lesson that wasn't appropriate. But what we did at the start, or what we did do last lesson, was remind ourselves what we mean by oxidation and reduction. We learned that there were 4 definitions of oxidation and reduction. You know, whether it's for oxidation, gain of oxygen, loss of hydrogen, loss of electrons, or increase in oxidation number. We learned that increase of oxidation number is the kind of true definition, and we wrote that down last time on the sheets. But this idea of oxidation number is a way of sort of accounting for movement of electrons in chemical reactions. This whole topic is redox, reduction and oxidation. They go in partnership. You can't have one without the other. It's all part of the kind of redox topic. So whenever there's a reduction, there's oxidation, and whenever there's oxidation, there's reduction. By assigning oxidation numbers, a kind of made-up thing, it helps us to understand what's happening in terms of electrons in chemical reactions. Right. So what we do is we kind of pretend that things are, well, we'll see in a bit, we sometimes have to pretend that substances that are actually simple covalent, we pretend they're really ionic. So we'll come to that when we get there. But what we're going to do is just trying to get stuck into this straight away by learning the rules for assigning oxidation numbers. And they are kind of written out on the sheet I've given you, but I'm going to start from scratch. So elements are always given oxidation number of 0. And I'll give you some examples. It could be simply an element of a metal or a noble gas, or it could be diatomic elements like chlorine, or it could be funky ones like ozone, which is 3 oxygens joined together. We assume that, well, all of these would have effectively a 0 charge, and so they'd have an oxidation number of 0. So all of the atoms, we're assuming they're all the same as each other, and they'd have a charge of 0 each. Okay, that's the first rule, and we'll do some practice of this in a sec. The second rule is that naked ions have an oxidation number that's equal to their charge. And what I mean by that is the ions that we're familiar with, those metal ions like lithium, which is a 1+ charge, has an oxidation number of +1. Oxidation numbers, I think I mentioned this the other day to you, but they start with the sign. We're supposed to always write the sign, then you have the number afterwards. Or it could be a 2+ ion, like magnesium would have an oxidation number of +2, aluminium, +3, or it could be the negative ions like chloride. Notice that the sign for the oxidation number, which I normally write above the element, it's not the charge, it is the oxidation number is above. It's given like so, or it could be a 2- ion, oxidation number of -2. Or it could be one of the metals that are transition metals that can have multiple oxidation numbers. So an example of that might be in iron chloride. There are 2 forms of iron chloride. Iron chloride that's got an ion that's a 2+ ion. We don't normally write the charge when writing it as a compound, but because each chloride is of course -1, the charge of that ion must be 2+. So the oxidation number will be +2, and we call that stuff iron 2 chloride because the oxidation number of the iron is 2+. We must always write the oxidation number of the metal in those cases, and this one, because you've got 3 chlorides, I'm sure you'd be able to work out that's iron 3 chloride because the iron's got an oxidation number of +3. Right, so naked ions have an oxidation number which is equal to the charge. Right, so the oxidation number numbers add up to the overall charge of the substance we're looking at. And I'm going to use the word species here, which you'll hear me use now and again in the course. Species covers everything, so it could be a molecule, it could be an ion, it could be a compound ion like nitrate or whatever. Overall charge of the kind of species we're talking about. And what I mean by that is most of the time you'll be looking at molecules that are zero charge, like carbon dioxide. So for carbon dioxide, the oxidation numbers of carbon and oxygen must add up to zero because it's a neutral molecule. So there is a 2- ion for oxygen, another 2- for oxygen, because oxygen, we'll see later, it's one of the rules that it's a 2- ion most times, and the carbon is +4 in this case. We'll see why in a bit, but that adds up to 0, or it could be something as simple as HCl, -1, +1. These are, remember, not the charges. We'll learn as we go along that these are the assignments if we pretend they're charged. Okay, I'll explain all the details of that in a sec. Or it could be something like methane, where each hydrogen, we'll learn soon enough, is +1, and we'll learn why. So we can work out what the the oxidation number of the carbon must be. In this case, to add up to 0, you've got to have a -4 oxidation number for carbon. So some elements can change oxidation number depending on the situation, depending on the molecule they're in, and that will be explained to you, I hope, reasonably satisfactorily. But the point is, I'm showing you now, that the numbers add up to 0 in these cases, or in the case of ions, like the nitrate ion, for example. Nitrate ion, I'm hoping you remember, is a 1-. So the oxidation numbers of the 3 oxygens and 1 nitrogen must add up to 1-. And we'll learn soon enough that the oxygen's nearly always -2. So those 3 oxygens together add up to -6. So something take away 6 is equal to -1. And so nitrogen in this case must be +5. So +5 take away 6 is -1, right? You'll do lots of practice of this. So I know this is all coming at you thick and fast. You'll do lots of practice of it. Another ion, we're going to do another example of a nitrate ion. This stuff we call, by the way, you've never heard it called this before, I don't think. You know it's nitrate, but its proper name, and what you must call it from now on, is nitrate 5. Why nitrate 5, do you think, as opposed to nitrate 4, would you say? Yeah?
Because its charge is 5.
Because it's, no, not its charge, its oxidation number is 5. Yeah, okay, its oxidation number is 5, exactly that. Whereas here, you'll start working these out yourself soon, but each oxygen's -2. In fact, you can tell each other what you think the oxidation number of nitrogen would be in this scenario. Given that something take away 4 is equal to -1, what's that something? It's year 7 maths. Tell each other. Something take away 4 is -1. Tell each other. Whisper it loudly so I can hear it as well. +3 or -3? +3. So this is what we call the nitrate 3 ion, right? Oxidation number 3. And we'll do, as I say, try not to make you panic, to see lots of stuff at the same time. We'll do one more of these. We'll do the carbonate ion, and one again that's on the list of ions that you will learn the formula and have already learnt the formula of. Lots of firm nodding. You know nitrate and carbonate and hydrogen carbonate and ammonium and sulfate and phosphate, right? All of those from memory. You know all the charges and numbers of oxygens in them all. So each oxygen's -2. We'll learn in a minute. And so what must the oxidation number, in this case of the carbon in carbonate, be? Something take away 6 is minus 2. Tell each other, please. Wow. Yeah. Everyone happy with plus 4? Yeah. So oxidation number is plus 4. Because the numbers all add up, right? So that's that rule. That's quite a useful rule. It's an important rule. And there's a couple of ways of putting this. Now, I'm going to put this slightly differently to the way that it's set out on the sheet. I think I'll put it in a way that's easier, slightly not as correct, and we'll come back to the correct definition, but this is the easier way of doing it, I think. So, hydrogen is always, put in inverted commas always, it's not always plus 1 unless H2, in which case it's 0, or with a metal, and then it's minus 1. So in every example you'll see, apart from H2 or say sodium hydride or lithium hydride or potassium hydride or calcium hydride, where the hydrogens are minus 1, I'll explain why in a minute, hydrogen is always plus 1. And you'll notice the exceptions are always present. So I'll direct you to the sheet straight away. Every single example on this sheet, hydrogen's plus 1, except here, because it's a metal hydride, there it's minus 1. So let's get that right straight away when we get to it. Okay. So I'm not going to give you any examples of that because I've already given you a couple actually. Another rule in inverted commas is oxygen is always minus 2 unless O2, of course, when it's 0, or in a peroxide. And a peroxide is when you've got 2 oxygen atoms joined to each other. So an example being H2O2. How many of you have ever bleached your hair? Some people have bleached their hair. This is the chemical you'd have used, hydrogen peroxide. Hydrogen peroxide, the hydrogens are going to be what? I've just told you a rule. What are the hydrogens going to be? Tell each other, nice and loud so I can hear it. Plus 1, yeah. So hydrogens are both plus 1. And because it's a neutral compound, they're going to add up to 0. So what must the oxygens be in a peroxide? Tell each other. Plus 1. Plus 1, take away something is equal to 0. What's the something? Tell each other so I can hear you. Yeah, cool, minus 1. So in a peroxide they're minus 1. It's not a trick question. You'll see that question come up in exams. Or with fluorine, and I'll come to that. So I'll give you an example of that. So in fluorine's always minus 1. So if you've got HOF, the fluorine's always minus 1, the hydrogen's always plus 1, and the oxygen therefore, if all that adds up to 0, must be, tell each other, yeah, 0. So the rules in inverted commas, but there are a few exceptions to them we must learn because they do love chucking and the exception your way. So the actual rule that underpins what I've just told you is that we assume what we're doing here, as I think I mentioned last time, is we're assuming that the compounds are individual ions, and we give the negative charge to the more electronegative atom. So what I mean by that, and I'm going to do this on a different page, on a different slide here. Let's use carbon dioxide as an example. So there's carbon dioxide. We know it adds up to 0, all of it, and you could argue this is, say, minus 4 plus 2 plus 2, but that doesn't work because oxygen's more electronegative than carbon, and so the minuses must be on the oxygen. So it must be minus 2 plus 4. If I do water, water is again another simple covalent compound. We pretend that it's ions, so oxygen would gain 2 electrons to make a 2 minus ion. The hydrogens would each lose an electron to make a 1 plus ion, because oxygen's more electronegative. And we've seen that so far with delta negative, delta plus, haven't we? But here we're now seeing it as pretend ions, if it were ions. Okay, so that's what's going on with those 2 rules I've just told you. And so what we're going to do now is do a bunch of examples. So we're going to work through this sheet together. If you've forgotten the sheet or lost the sheet, I don't have any spares, I don't think. I should pause the video a sec. We'll do a few of these together. So we'll start on the top line. We might have done some of these in class last time, I think. But the iron here is 0 because it's an element. We did this just before, so it's plus 3 because it's each chloride is 1 minus. The reason chloride is 1 minus is because it's the more electronegative of the elements there. So either had to be plus 1 or plus 3. The chloride had to be either minus 1 or plus 7. Well, it's all going to be plus 7. This one, iron, is plus 2. This one is a bit harder. So when you're working these out, please don't write minus 8 above the oxygen. Please write 4 lots of minus 2, or write minus 2 4 times. Potassium is a naked ion. It's group 1, so it's plus 1 and plus 1. All we've got to do then is work out what the ion is in the middle there. So 2 take away 6, we've got so far, we're going to have a something in the middle there. So what would that be? Have a little chat, work it out, have a think. What are we going for? We're going to get votes for plus 6 and plus 4. So 2 plus 4 take away 6 is equal to 0, isn't it? So it's plus 4 there. You'll do lots of this, you'll get the hang of it. So that's plus 4. And this one looks complicated but isn't. We know that water's a neutral molecule, or we could look at it differently. We know that 2 pluses and a 2 minus all add up to 0. So if that lot all adds up to 0, the iron must be plus 2 to make that make sense. You'll do much more on these things called complex ions next year, but that's plus 2, so don't fret about those too much. But the iron's 2 plus with 6 neutral waters hanging around outside it. We'll do the next level as well together, and then you do them on your own. The chlorine is what? I've done some dodgy maths there. Oh, it's 8. God, I'm doing 4. Yeah, sorry, plus 6. Yeah, thank you. Sorry, thank you for that. Please, if I will do things like that now and again. Please do call me out on it. All right, I won't take offence. I'd much rather you told me than let me get it wrong. So chlorine there is 0. Here we've got 3 lots of minus 2. So for the oxygen, I haven't written that exactly above. So something take away 6 is equal to minus 1. So what could that chlorine be? You can have a little chat about it, see if you can agree. Something take away 6 is minus 1. Something take away 6 is minus 1. What do we think it is, please? Not many people are saying it, but it's plus 5. And then the oxygen here, so this one together, something take away 2 is minus 1. What take away 2 is minus 1, everybody? Plus 1, right? That's plus 1 then. Good stuff. And then this one, right, there are 7 2 minuses. Let's write those above. 7 lots of minus 2, I should say. So the chlorines must add up to plus 14, right? So what must each chlorine therefore be, Isabella? Yeah, plus 7. And then finally, same sort of idea, 3 lots of minus 2, so that's minus 6 altogether. So each chlorine must be plus 3. Right? Can you have a go at these, please? Go as quick or as slow as you like. I'll come around and help you. I'll pause the video. What I'm going to do is quickly write up the answers to all of those, so you can see them on the screen. Then do the questions on page 3 and 4. Work on another one for now. So if we're thinking about hydrogen cyanide, which by the way I wouldn't recommend breathing in, how do you work out what its oxidation numbers would be? Well, if this is the dot cross diagram, the Lewis structure for hydrogen cyanide, which it is, which you can work out from the rules that we've learned before, carbon is more electronegative than hydrogen. So carbon gets those electrons, if you like, which is why hydrogens are always +1. The nitrogen is more electronegative than carbon, so these 6 electrons all head over to nitrogen, 3 of which were nitrogens already, 3 more go to nitrogen from the carbon, so that one's -3, and then you're left with what carbon is. Okay, so what's the answer? +2. That's the answer. Right, good question. If I've made a mistake anywhere, give us a shout. I don't think I have. Did those a bit quick. Check your answers the same as mine there. Okay, I'm bored, so we're going to move on. I think what we need to do actually anyway is practice these at a separate time. You've got the hang of it. Most of you got most of those right. That's what's going around. I was checking. It looked like you got the hang of this. What I kind of need you to do now is to maybe do a bit of practice on some of these if you can. I know we want to concentrate on the bonding topic. We'll come back to those, practice them again so that they're cemented, a bit of space practice on those. So leave the rest of them, maybe do a few in a week or two over half term if you can face it. We'll certainly do the rest of those in time. It'd be good to have a little break before doing them. And so what we're going to do now a little bit is writing half equations, something you think you know how to do, but I promise you've got no idea. Okay? This is an important skill. This comes up a lot in a number of different ways, and I'll probably come back to it a couple of times to practice it with you in kind of exam style scenarios as well, but I'm just going to teach you how one goes about balancing half equations. So you've seen plenty of these in the past, very simple ones, but we're going to do much more complicated ones from today. Everyone ready to go with this? You're going to need to be with me on this one. So writing half equations. Half equations, remember, always include electrons because we're showing either an oxidation or reduction taking place. So this is half equations are kind of one half of the process that's happening in a redox reaction. If it's a reduction going on, we had a look at these last lesson anyway. If we had a reduction going on, it's something having electrons added to it, and then oxidation is when something is losing electrons, and we show that in a half equation. We can combine half equations together, which we'll learn probably next lesson, to form an overall ionic equation, but that will not have electrons in it because they'll all cancel out, they'll all be transferred from one place to another. So there are some rules that we have to learn on balancing half equations, and I'll give you a chem sheet next time I see you, which will have the rules set out slightly differently to the way that I'll show them to you, but so there's more than one way of doing this, but it boils down to the same thing in the end. So step 1 is balance the element that changes oxidation number, and I'll do loads of examples in a sec so you'll get the hang of this, what I mean by it. Step 2 is balance oxygens using water, and you'll see that most of these redox equations happen in water, and the water actually gets involved in the reaction, as you'll start to see. Lots of redox happens in water, but you might find that hydrogens aren't balanced as well, so we often find we have to do redox reactions in the presence of either acid or alkali. IB we concentrate only on acid, so we balance hydrogens using H+, which is what acids release, remember. Finally, we balance charges using electrons. Now that's how you balance the equation, but there's a fifth step which I usually fail to persuade people to do, but I'm hoping that some of you will at least listen carefully at this point and remember this final and important step, which is check. And I will, before this lesson ends, deliberately get one of these. I might get some wrong by mistake as well, but I'll deliberately get one wrong, and it'll be the checking step that allows us to see we've got it wrong. All right? Just warn you, this time I'm trying to make a mistake, which I sometimes do as well. So check equation by comparing oxidation number with number of electrons transferred. That will make no sense to you, any of that, until I've shown you some examples, but you must learn the sequence. Some of you are really good at writing out flashcards as you're going along. This is absolutely the sort of a thing that will go on a flashcard and you'll try to memorize, right? Between now and certainly before we finish the redox topic, but ideally sooner rather than later. So let's do a couple of simple examples and then we'll move on to some more difficult ones, and we'll do a whole bunch of these when I next see you. Right, so we'll do a simple example. So lithium going to lithium plus, right? Right, the lithium clearly is changing oxidation number as it goes from lithium to lithium plus, 0 here, plus 1 here. And with the checking, we've got 1 lithium on each side. We've done that. There's no oxygen, so we don't need to worry about that. There's no hydrogen, so we don't need to worry about that. We balance charges using electrons. Let's practice that step. Now, which side do you put the electron or electrons on? Well, you always put them on the more positive side. You put them on the side to help match up the charges on both sides. So the left hand side has got a charge of 0, the right hand side at the moment has got a charge of +1. So the right hand side is more positive, so we add the electron to the right hand side, and now we've got the same charge on either side. That's that first one done. But step 5 is check the equation by comparing oxidation number with number of electrons transferred. This is oxidation number 0, oxidation number +1. That's a 1 electron loss. Oh look, we've got 1 electron that's been lost. Let's find that one's checked, it's good, right? Really simple. And we'll do a slightly harder example, one you've seen before. So chlorine turning into chloride, okay? Something that happens in electrolysis. Oh, well, it's the other way around to what you see in electrolysis, but it doesn't matter. So the first step is to check or to balance the element that's changing oxidation number. Well, that's the chlorine. We've got to balance that. There's 2 chlorines on the left, there's only 1 on the right. So we balance that by putting a 2 in front of it. There's no hydrogens or oxygens to worry about, so we can skip step 2 and 3 here. But we've got to balance the charges using electrons. We put the electrons on the more positive side, as always, which is the left hand side, which has got a charge of 0. The right hand side's got a charge of -2. So we're putting 2 electrons over here. 2 electrons required to reduce 2 chlorine atoms to 2 chloride ions. We'll do a more complicated example now, a common one that we'll see lots of times. You probably haven't seen before. This is a substance called manganate 7. Why do you think it's called manganate 7? Let's consider that name for a second. Manganate 7. Why do you think it's called manganate 7? So Cameron, start us off.
The manganese element.
Right, so the manganese element is present. Right, but why is it manganate? Someone else. Why is it manganate rather than manganese? Then what's going on there, Gabriel? Oxygen present gives it an 8, like carbonate, sulfate, phosphate, manganate, chlorate, bromate, all have oxygen present. Lots of people forget that little rule. And the 7 refers to what, please, Isabel? Of the, exactly, yeah, 2, 4, 6, 8, and there's a -1 there. Right, so it's manganate 7. if you use that in a chemical reaction, it's an we'll learn soon enough that it's an oxidizing agent, which means it gets reduced. It gets reduced to something called manganese 2+. Right, so first of all, step 1, balance the thing that's changing oxidation number. So are the manganeses balanced on each side? Yes or no? Thumbs up, thumbs down. Are there the same number of manganese elements on both sides? Thumbs up or thumbs down? Yeah, there's one on each side, isn't there? That's right. Are there the same number of oxygens on each side? No. So what we're going to do, Damien? And how we're going to do that? So how many waters am I going to put and where am I going to put them? Which side? Yep. So we add 4 waters over here. And then we're going to balance the hydrogens using H+. So where am I going to put the hydrogens and how many am I going to put? Please. You put 8. That's right. So 8 H+. And then we've got to balance the charges using electrons. We've just got to plot up the charge on each side, right? So on the left-hand side, -1 plus 8 is overall +7, and on the right-hand side it's +2. So how many electrons are we going to add to start with? Show me with fingers. How many electrons we need to add to this equation? It's going from 7 to 2, so it's 5. And which side are we going to put them? Point left or point right? We put them on the more positive side. Which is the more positive side of the reaction? Which is the more positive side of the reaction? Right. So we add 5 electrons. I haven't left myself enough room. I normally write it afterwards, but I'm going to have to put it over here to make it fit. 5 electrons. And then we check, don't we? We check using like we said we should do in step 5. This is oxidation number +7. This is oxidation number +2. That's a 5 electron change, and that's right, isn't it? Yeah. Okay. We're going to do another one. You're going to do a few of these by yourself in due course. So we're going to use another common oxidizing agent, something called dichromate 6. Why is it called dichromate 6, please, Laxager? Oxygen's present, so it's not chromium, it's chromate. And why dichromate 6? Yeah, chromium's got oxidation number 6, simple as that, right? So we've got chromium on both sides. We then balance the oxygens using water, with 7 of them. We balance the hydrogens using H+. And then we balance the charges using electrons. So we've got 14 on this side, take away 2, so we've got +12 on this side and +3 on this side. So we add 9 electrons there. And then we check to see that's right, don't we? How do we check to see it's right? Talk us through if it's right, please, Arsene. Right, so what's the oxidation number of the chromium? It's dichromate 6, yeah, that's right. And this is chromium 3. And so it's a 6 electron. What? Huh? Is it right? No. So the checking step saved us. I warned you that I was going to make a mistake. This is the mistake I made. Cameron spotted it because he was practically waving at me. What's the mistake that I made? Can you, without one of you telling me, can you each tell each other what mistake I've made along the way there? Deliberate mistake there somewhere? How many of you spotted the mistake as it was going? Which step did I miss out? Missed out step number 1. So what should I have done, Adam? Can you? I don't like the word it.
Or balance chromium.
Balance chromium. So what do you want me to do then?
Add 2 to the right side.
Add 2 to the right side, and how many electrons must be here rather than?
6.
So it should be 6 electrons here, and then you've got +6 going to +3 twice, which is 6. So that step 5 works now, right? So it's +6 going down to +3. It's a reduction. It's happening twice because there's 2 of them, and so that's how you balance half equations. I'm going to scribble down one for you to do by yourselves, and that's probably where we'll stop. I'll scribble it down now though. So can you have a go at balancing that half equation, please?